Hi, and welcome to 11.3 Ohm's Law. Now that we know about voltage, current, and resistance, we can relate them together in this handy formula that was developed by this guy, German physicist Georg Ohm. He actually used to be a physics teacher, and he came up with this formula. I am particular to this version of the formula, which is also written down here. I don't know if you can see that. I equals V over R. But in your reference table, it's R is equal to V over I. Let me tell you why I equals V over R is my favorite version of that formula. If we continue our discussion, our analogy of electricity to water, like we did in 11.1 current, we could look at the formula I is equal to V over R, like current in a stream. Well, if that stream was completely flat, there is no difference in the height from one side to the other. It's just the same height on one side of the stream and the other side of the stream. The water has no reason to flow one way or the other because it's the same height. It's just a nice, serene, calm, maybe a nice little pond. Can you tell that I want to be outside right now? Yes, it would be very nice to look at a nice serene pond right now. But that's not what we want in our circuit. In our circuit, we want there to be some current. So how do you get the current to flow in a river? You need there to be some potential difference. You need there to be a height difference. And if you remember back to 10.6, when we talked about voltage, we talked about how you could think of voltage as the difference in two positions in a potential field. So with the water, you have one position and another position. The water flows to the lower potential naturally. That's where it wants to go. And we're going to try to do the same thing with our electrons. We want to build the electrons up to a high potential, maybe using a battery that is a voltage source. And the electrons will naturally go down to a lower potential. And then as they go through the circuit, they go to the other side of the battery when the battery then pushes them back up to a high potential and the electrons flow down, just like the water flows down in a waterfall. So in a waterfall, you're on the top of the waterfall and then there's a height difference. You go down in the gravitational field, and the water naturally flows from high potential to low potential. Before, there was no potential difference. And that's basically what causes there to be a current. You need there to be a potential difference or a voltage, and the higher the voltage, the more current you're going to have. There's going to be like a steeper incline because you could just have a gradual hill where the water's flowing down. Or if it's a very steep hill, the water will flow faster. And if it's a very shallow hill or nothing at all, you're going to have very little current. And that's why it's a direct relationship in this formula. And that's why I like this version the best, because you could really see that the higher the voltage, the higher the current. So where does resistance come into play with this? Well, would you expect the same thing to be true? If we increase the resistance, is that going to allow current to flow as easily? I would say no, the opposite is true. In order to get more current, a faster current going, you need to have very little resistance. We don't want there to be a resistance of the flow. We don't want there to be like sticks in a river, where let's say there is a little bit of flow here, and if we put sticks in a river, a beaver comes along and adds some resistance to the flow, it's going to slow down the current, and eventually a dam could build up, let's say. But that's the idea there, is that the more resistance you have, the less current there is. And that's why it's an inverse relationship in our formula. And that's why that's my favorite version of the formula, because for me it's easy to conceptualize what is happening with the current. To get a faster current, you want to push it with more voltage. To get a faster current, you want there to be less resistance. But you could use I is equal to V over R, And if you cross multiply, you get V is equal to I times R. And then if you divide and solve for R is equal to V over I. And like I said, this is the one that's going to be in your reference table. You could really use any of them. So it depends. If you're looking for current, use this one. If you're looking for voltage, use this one. If you're looking for resistance, use that one. Okay, so let's do some problems. They have an example here for you. I don't really give you a lot of space in this worksheet. Let's see how we do. So it says how much current. So they're looking for I, the 9-volt battery, and the resistance of the bulb is 3 ohms. So I would do I is equal to V over R. I is equal to 9 divided by 3, and you get 3. Units for current are amps, so 3 amps. Now it's saying how much current is in a circuit that includes a 9-volt battery and a bulb with a resistance of 12 ohms. So it's going to be the same thing. Still doing I is equal to V over R. So now you get 0.75 amps. All right, so it's a circuit contains 1.5 volt battery and a bulb with a resistance of 3 ohms. Calculate the current. And now you get 0.5 amps. It says a circuit contains 2 1.5 volt batteries for a total voltage of 3 volts. And that's how we're going to add the batteries together. This is actually, the batteries are connected in series with each other. So you just straight up add the voltages if there's 2 batteries. 1.5 plus 1.5 is 3. And the bulb is 3 ohms. Calculate the current. And 3 divided by 3 is 1 amp. All right, now it says what is the voltage of a circuit with 15 amps of current and a toaster with 8 ohms of resistance. So this one's a little different. The current is 15 amps. Now they're telling you what the current is. They're telling you the resistance is 8 ohms. And what are they looking for? It says what is the voltage? So you have a choice. You could continue to do I is equal to V over R. But since we're looking for the voltage, I'm actually going to use this version of the formula. V is equal to I times R, and this is going to be 15 times 8. So you get 120 volts. Oh, I was going to ask, what is the unit for voltage? Don't forget, it's just volts, okay? So it might look weird, V is equal to 120 V. If you were just looking at this instead of a variable is equal to 120 times the variable, well, V must be 0. I don't know. Don't confuse yourself. For voltage, it's a little weird. V is equal to 120 V. Different from like I is equal to 120 A. For the current is equal to 120 amps. Okay, so moving on. It says a light bulb has a resistance of 4 ohms and a resistance of 2 amps. What is the voltage across the bulb? All right, so again, we're looking for the voltage. And you could use V is equal to I times R. And we did 2 times 4. So you get 8 volts. And it says how much voltage would be necessary to generate 10 amps of current in a circuit that has 5 ohms of resistance. You can see where this one's going. The voltage is going to be 50 volts. I am going to pause here, and actually a student of mine came up with this. It's kind of a nice way to remember the formulas, and we'd seen something similar to this in the past. They made a triangle like this. You seen this before? And let's see, if we want, what's the one that they're multiplying? V is equal to I times R, right? So you put the I down here, I times R, that equals V. And if you're looking for I, well, that's V over R. And if you're looking for R, well, that's V over I, which is the one in your reference table. And if you're looking for V, then it's I times R. So this little triangle thing, you've seen it for probably density. And if you remember, I think we did it for velocity too in the beginning of the year. It'll work for any equation that you have something that looks like something is equal to something divided by something else. You can do this triangle type of thing. You could even make a triforce. But anyway, let's continue on here. Thank you to that student for reminding me that you can do that. That was a good application. So it says how many ohms of resistance. So now they're looking for the resistance. Okay, and the circuit has 120 volts, and the current is 10 amps. So what was the one for resistance again? And again, you could use any of the formulas, any of the situations, but if they're looking for the resistance, let's use the one that's already solved for the resistance, and that is R is equal to V divided by I. So that's equal to 120 volts divided by 10, and you get 12. Well, what are the units for resistance? 12 ohms. All right, it says an alarm clock, 0.5 amps of current, and 120 volts. What's the resistance? You get 240 ohms. Now it says a calculator is uses 4 1.5 volt batteries, and they're telling you the total voltage is 6 volts. If the current in the calculator is 4 amps, what is its resistance? So 6 volts divided by 4 amps, that'll give you 1.5 ohms of resistance, 3 halves. Okay. You have a large flashlight that takes 4 D-cell batteries. If the current in the flashlight is 2 amps, what is the resistance of the bulb? And they're saying 1 D-cell battery is 1.5 volts. So this is a little tricky. They've been leading you into this idea. We have 4 of them, so the voltage is equal to 4 times 1.5 volts. So the total voltage is 6 volts. So if you didn't get that on the answer key, it's because you probably plugged in 1.5 or maybe even 4. You had to do 4 of the batteries times 1.5 volts each. So that's the trick with that one. I is equal to 2 amps. What is the resistance? It's going to be 3 ohms. Now it says what happens to the current in a circuit if a 1.5 volt battery is removed and replaced by a 9 volt battery. Well, if we look back to our analysis with the river in the beginning of the video, what we're doing is we're increasing the voltage. We're making it like a steeper hill. And when you increase the voltage, what's going to happen to the current? Well, even if you look at just the pure mathematical relationship, you want to find I is equal to V over R. And you could see that the voltage, if the voltage increases, the current, because it's a direct relationship, also increases. So this one is a little weird. They didn't tell you what the resistance was, so you can make up a resistance and do a calculation for the 1.5 volts, use that same resistance, do another calculation now for 9 volts. What happened to the current? I bet you that the current increases because it's a direct relationship. And there you go. So that leads you into thinking about number 13. It says, in your own words, state the relationship between resistance and current in a circuit. So looking back at my favorite formula here, what can we say about the relationship between resistance and current, R and I? How are those two things related? Well, I would probably say that they're inversely related. The bigger the resistance, the less current there is. So, but me, I'm going to be fancy and say it's an inverse relationship. Number 14 says, in your own words, state the relationship between voltage and current. So if we looked at the same formula, kind of like we said in number 12, between voltage and current, what's the relationship? I would say it's a direct relationship. Now it says, what could you do to a closed circuit consisting of 2 batteries, 2 light bulbs, and a switch to decrease the current? And it even gives you a hint. You have the ability to take out any of the elements. So the circuit might look like this. Let me draw it down here. You have a battery for number 15. This is for 15. You have a battery, and it's a closed circuit. Actually, there's 2 batteries. Closed circuit with 2 light bulbs. Okay. Right there. And it's a closed circuit. Oh, and there's a switch too, so I could either turn the circuit on or turn the circuit off. To draw the switch symbol, you draw it open, because if it was, to make current flow, it has to be a closed switch like that. But how do you tell if there's a switch there? You can't tell now, it just looks like a wire. So this is the symbol for the switch. Let's assume the switch is closed. What do they want you to do? Decrease the current? Well, if you wanted to decrease the current, would you take out a voltage source or would you take out a bulb? And why? Well, for me, if I is equal to V over R and I wanted to decrease the current, by taking out a battery, that decreases the voltage. And that's exactly what we want. If I take out a bulb, that decreases the resistance. And since it's an inverse relationship, that would actually increase the current. So looking at the formula here kind of helps answer this question, maybe drawing a picture. So if we wanted to decrease the current, we got to decrease the voltage and take out one of the batteries. Now there is less voltage being supplied to the circuit, so I would take out a battery. Okay, for 16, it's kind of a similar situation. We're thinking about the circuits themselves now. Instead of just using the formula, plugging it in, we got to think about the circuits. So let's see. What is it? What is the situation? It says you have 4 batteries, okay? A 1 ohm bulb, a 2 ohm bulb, a 3 ohm bulb. Draw a circuit you could build to create each of the following currents. So for A, they want 1 amp of current, 2 amps, 3 amps, 6 amps. Of the 4 batteries and the 3 bulbs, how would you get these currents? There may be more than one possible answer for each, so more than one circuit might give you a current of 1 amp. And it says, hint, remember you can add the voltages of the batteries together, so your circuit may have a voltage of, so they're telling you, it could be increments of 1.5, 3, 4.5, or 6, depending on how many batteries you put in. Well, for part A, they want a current to be 1 amp. So if we want our current to be 1 amp, we better have the same voltage and the same resistance, right? Because we want them to divide out and get 1 amp of current. So I have 1.5 volt batteries, and these are whole numbers. So I know I can't use one battery to get 1.5, and I can't use 3 batteries to get 4.5. It has to be increments of maybe 3 or 6 using these numbers, 1, 2, and 3. So you could use all the, you could use everything. If you use the 4 batteries, you get 6 volts. And if you use all the bulbs together, you get 3 plus 2 plus 1, so that's 6 ohms, and that'll give you 1 amp. But I'm kind of lazy. I just want to do, maybe I'll do 3 volts and just the 3 ohm bulb, or maybe the 1 ohm and the 2 ohm bulb. But that'll also give you 1 amp. So like it says, there's many different ways to do it. And this is how I chose to do mine. This is 2 1.5 volt batteries, so that's a total of 3 volts. And I'm choosing to put the 3 ohm resistor here. So we did I is equal to V over R. 3 volts divided by 3 ohms, that's equal to 1 amp. So this is for 1 amp. Okay. Now let's do part B. So B wants you to have 2 amps of current. So if I is equal to V over R and we want to get 2 amps, how would we do that? Well, the voltage better be twice as big as the resistance. So if the voltage is 2 volts and the resistance is 1 volt, that'll give you 2 amps. If the voltage is 3 volts and the resistance is 1.5, that'll give you 2 amps. But let's see, what can we use? We'll probably have to do maybe 6 volts and 3 ohms. That would give us 2 amps. So how would we do that? We would need to have 4 batteries and either the 1 ohm and the 2 ohm or just the 3 ohm bulb. Either one would work. So there's more than one right answer for this. Okay, so we have 4 1.5 volts for a total of 6 volts. Divided by 3 ohms, that gives you 2 amps. Good, nice. Now for part C, we want to have a current that is 3 times as big as the resistance to get a current of 3 amps. this has to be 3 times that. So we have a 1 ohm bulb. So we have a 1 ohm bulb and we have 3 volts. So that would actually work. We could have 3 volts over 1 ohm. That'll give us 3 amps. Could we do 6 volts over 2 ohms? Yeah, we got a 2 ohm bulb. So again, more than one right answer for this. There might even be more. But I'm going to do this one where it's 1.5 volts plus 1.5 volts for a total of 3 volts. And this has to be the 1 ohm bulb to get 3 amps. So for part D, okay, maybe you see where this is going to go. They want 6 amps. So the voltage has to be 6 times as big as the resistance in order to get 6 amps. How would you get the voltage to be 6 times bigger than the resistance? Probably just like that. I would have all 4 batteries for a total of 6 volts, 1.5 times 4, and then I would use the 1 ohm bulb to get 6 amps. And I'm pretty sure, given those circuit elements, that's probably the only answer for part D. So it should look like this. Same thing as part B, 4 batteries for a total of 6 volts. But to get 6 amps, 6 divided by what is 6? 6 divided by 1 is 6. So that we better use the 1 ohm bulb instead of the 3 ohm bulb. Alright, hopefully you got a good start with Ohm's law. And you know what? It's a kind of a big deal because now we got all 3 parts. Now we know voltage, we know current, and we know resistance, and we're almost ready to analyze some circuits. This is just building. We're building all the different tools that we need in order to do circuit analysis, which is really what Unit 11 is about, series and parallel circuits. But before we do that, we have to talk about electrical work and power, which is in the next video. Okay, have a great day.